Chapter 11, the t-test family. Section 11.1, Purpose and Interpretation of the t-test. The t-test is one of the most important and most commonly used inferential statistics. There are several specific implementations of the t-test that depend on the nature of the data, so the number of groups, sample sizes, variances, and so on, but they all share a common framework. In this section, you will learn this fundamental framework, how to interpret the t-test, how to derive a p-value from a t-value, and the assumptions that underlie t-tests. In later sections, I will introduce the specific variants of t-tests for different data situations, so one sample versus two sample, equal versus unequal variance, and so on, and non-parametric alternatives to use when your data violate assumptions of the t-test. There are also members of the extended t-test family that I will present later in the book. For example, the t-test for statistical significance of correlation coefficients. Section 11.1.1, the purpose of a t-test. The purpose of a t-test is to determine whether the mean of a sample is different from the specified null hypothesis value. There are three scenarios in which you would use a t-test described below and visualized in figure 11.1. Although these may seem like distinct situations, the t-tests used to evaluate these situations are conceptually and mathematically similar. Scenario 1, a one-sampled t-test. In this scenario, you have one data sample, and the objective is to determine if the sample mean significantly deviates from a predetermined null hypothesis value. This paragraph refers to figure 11.1a. Figure 11.1 panel A is titled One Sample and shows a scatter plot with data index on the x-axis, data value on the y-axis, and a bunch of gray dots that are scattered all over the place. There is a horizontal black dashed line at somewhere around a third of the way up on the y-axis, such that most of the data points are above that line, but a sizable minority of data points are below that line. Back to the text. For example, perhaps the dashed line in the figure panel is IQ equals 100, and the data values are IQs of children in a particular classroom. Clearly, not all of the data samples are above the null hypothesis value, but it is possible that the average is significantly greater than the null hypothesis value. Scenario 2, paired samples t-test. In this scenario, you have one group of individuals that were measured twice. For example, imagine a study in which a research team recorded sales volume from 30 companies before and after a corporate team building retreat. Some companies experienced an increase in sales volume while others experienced a decrease. The question is whether sales volume increased on average across the 30 companies. This paragraph refers to figure 11.1b. This panel also shows a scatter plot. However, it's different from the one in panel A. Here in panel B, which is titled Paired Samples, we have two columns of data points, one corresponding to pre or before the treatment was applied, and the second column labeled post or after the treatment was applied. The dots have different colors, different grayscale intensity values, and there are lines connecting each dot in the pre column to its corresponding location in the post column. So what you can see is that many lines go up from pre to post. Some of the lines go down from pre to post. Scenario 3, independent samples t-test. In this scenario, you have two separate groups of individuals and want to determine whether the means of the two groups differ. Because they are different samples, the sample sizes and variances might differ, although we are only interested in testing for differences in the means. An example is a study that compares exam scores from students who attended a study session in Group 1 to those who did not attend the study session in Group 2. The goal is to determine whether attending the study session had a significant impact on the students' exam scores. The two lines in panel C depict histograms of exam scores from the two groups. This paragraph refers to panel C, figure 11.1, which shows two lines that represent histograms for Group 1 and Group 2. The y-axis is labeled count, the x-axis is labeled exam score, and the panel depicts that the two histograms are both roughly Gaussian shaped with one peak. However, Group 1 is narrower and a little bit to the left, and Group 2 is wider and a little bit to the right. Section 11.1.2, General t-test formula. Equation 11.1 shows a general formula for a t-test. Later in this chapter, you will learn modifications to this formula for the specific cases I highlighted above, but this formula is a template for all members of the t-test family, and I encourage you to commit it to memory. Equation 11.1 reads T sub df equals the fraction. In the numerator, we have x bar minus h naught, and in the denominator, we have s divided by the square root of n. Back to the text. df is the degrees of freedom, h naught is the null hypothesis value, s is the sample standard deviation, and n is the sample size. The denominator is the standard error of the mean, abbreviated SEM, which you learned about in section 9.3. A few remarks on the t-test. Remark 1, a t-test against an a priori chosen value is a one-sample t-test. A typical h-naught value is 0, that is, a one-sample t-test is often used to determine whether the mean of a sample is different from 0. In the children's IQ example I mentioned earlier, the h-naught value would be 100. Remark 2. A t-test between two groups is called a two-samples t-test. Two-samples t-tests can be paired or unpaired with equal or distinct standard deviations and sample sizes. These lead to modifications of the t-test formula, and I will discuss them later in this chapter. Remark 3. The t-test is based on means and standard deviations. A t-test can be statistically significant even if some data points show the opposite effects from the group mean. Imagine, for example, a significant t-test comparing heights of men and women. On average, adult men are taller than adult women, but not every man is taller than every woman. Remark 4. One way to conceptualize the t-test equation is as a normalized difference of means. In other words, the average effect scaled by the variability. This conceptualization links the t-test to the general concept of a test statistic as a signal-to-noise ratio. Another way to conceptualize the t-value. The numerator is the mean effect and the denominator is the standard error of the mean, which reflects how precisely we can estimate the population mean. A smaller SEM indicates that we can more accurately estimate the population mean, which increases our ability to discriminate between the sample mean and a given null hypothesis value. The numerator and the denominator have the same units, which gives a unitless measure of the distance between x bar, the sample mean, and h naught, the null hypothesis value. Remark 5. The t-value is influenced by the sample size. In particular, increasing the sample size will increase the t-statistic, even if the mean and standard deviation do not change. This means that the distribution of null hypothesis t-values depends, in part, on the sample size. Indeed, imagine placing the square root of n factor in the numerator. The t-value will increase simply with increases in sample size, even if the mean and standard deviation remain the same. That is why we need to know the degrees of freedom to associate a t-value with a p-value. Remark 6. The sign of the t-test is somewhat arbitrary. You can write x bar minus h naught or h naught minus x bar. The magnitude of the t-value and its associated two-tailed p-value will be unaffected. You can choose the sign to facilitate interpretation. For example, if you are testing for an increase in exam scores after reading a textbook, it makes sense to have a positive t-value. On the other hand, if you are testing for decreases in postoperative pain with a new surgical technique, then a negative t-value is more interpretable. Section 11.1.3, Degrees of Freedom of t-tests. Remember that degrees of freedom, indicated df, is the maximum number of data values that can independently vary in a sample dataset. Because the t-test involves testing sample mean, the df associated with a t-value will be the number of data values that can vary given that we know the sample means. So for a one-sample t-test, because there is one sample with one mean, the df is n-1, where n is the sample size. Paired samples t-test. You will learn later in this chapter that the paired samples t-test is actually the one-sample t-test in disguise. Spoiler alert, subtract the two measurements to get one data value per individual. This means that the df is again n-1. Independent samples t-test. The df of a two samples t-test is n-1 plus n-2 minus 2, where n-1 and n-2 are the sample sizes of the first and second groups. Why minus 2? Well, there are two samples and two means. So the total df is n-1 minus 1 plus n-2 minus 1, which is then simplified. In some cases, the degrees of freedom calculation is more complicated to incorporate differences in sample variances. More on this later. In terms of typographical formatting, t-values are reported with the df either in subscript or in parentheses. For example, a t-value of 2.56 with 13 degrees of freedom can be written as t sub 13 equals 2.56, or as t parenthesis 13 end parenthesis equals 2.56. Which format to use is sometimes a matter of personal preference, sometimes dictated by the publisher. This book is self-published, so I have total freedom over the formatting. As proof, I here wrote some ridiculous-looking formatting, which is a visual-based joke that wouldn't make sense by listening to this audiobook. Section 11.1.4, p-values from t-values. If h naught were true, then we expect x bar equals h naught. Alternatively, x bar minus h naught equals 0. This would make the t-value exactly 0. But of course, with sampling variability and noise, we cannot expect t-values to be exactly 0. And if we were to collect lots and lots of samples, we would expect the h naught t-values to have some distribution around 0. Well, you've already computed and visualized a family of t-PDFs in exercise 10.3. And if you haven't done that exercise yet, I recommend working through it before proceeding in this chapter, or at least flip back to page 331 to look at the distributions. As a quick reminder, figure 11.2 shows a t-value PDF for one df parameter. The question we ask when evaluating the statistical significance of a t-value is this: what is the probability that a t-value more extreme than our empirical t-value could have been observed if the null hypothesis were true? Important. The x-axis of the t-PDF is not data values, nor is it expected sample mean values. It is the t-value, which is unitless due to the standard deviation in the denominator. This means that you could scale the data by some arbitrary amount, or change the data units, like from meters to micrometers, and the t-value and associated t-PDF would remain unchanged. How do you get p-values from a t-value? The PDF of a t-distribution comes from the following equation. I am not going to read these two equations. They are very complicated and long and actually not that relevant. Because the text continues after these two equations, please don't ask me to derive those equations from first principles. That's something you would learn in an advanced course on mathematical statistics. The point here is that p-values come from formulas, most of which are dense and complicated, and which provide basically zero insights or useful information about how to use or interpret p-values. PDFs for other distributions you'll use in statistics can be found online, for example, on Wikipedia or on the scipy.stats library website. I won't say not to look them up, but I will warn you that staring at those equations is unlikely to make you a better statistics practitioner. Instead, you can focus on the idea of determining statistical significance and deriving a p-value, which I introduced in Chapter 10. Compute the probability of observing a t-value as large as or larger than the t-value observed in the real data. Now let's return to the practical interpretation of the question, how do you get p-values in Python or R? In Python, you use the functions available in the scipy.stats library. In R, you use functions available in the base package. Either way, you need to know the t-value and the df, both of which you compute from the data. The p-value comes from evaluating the CDF at the observed t-value using the following code. The Python function is 1 minus stats.t.cdf. The first input is the t-value. The second input is the degrees of freedom. In R, the code is 1 minus pt, the function pt, and the first input is the t-value, and the second input is the degrees of freedom. Back to the text. The p-value for this t-value of 2.1 with 13 degrees of freedom is 0.028. I imagine you might have two questions about this code. First, why use the CDF and not the PDF? The reason is that we're not interested in the probability of obtaining an H0 t-value that exactly equals the t-value in our empirical data. Instead, we're interested in the probability of obtaining a t-value that is as extreme as or more extreme than the value we obtain in real data. For example, we don't want the probability of t equals 2.56, given that the null hypothesis were true. We want the total probability of the H0 t-value being anywhere between 2.56 and infinity. And for the negative tail of distribution, the total probability of the null hypothesis value being anywhere between minus infinity and minus 2.56. Second, why use 1 minus CDF? Remember that the CDF is the cumulative sum of all probability values less than the specified value, that is, to the left of the distribution. So for a positive t-value, we want to know the probabilities greater than that value, so to the right in the distribution. And if the total area of the PDF is 1, then the area to the right of some value equals 1 minus the area to the left of that value. In fact, the code that I described above is valid only for the one-tailed p-value to the right of the distribution. A two-tailed t-test would require computing the areas of the probability distributions of both the left and the right sides. So corresponding Python code would look like this. The first line of code is p-val L for left equals stats.t.cdf. First input is minus the t-value, and then the second input is the df. This gives us the area of the left tail. The next line of code is p-val R for the right. That is 1 minus stats.t.cdf of the positive t-value, and that gives us the area to the right of the tail. And then we have the p-value 2 for the area of both tails. That is the sum of p-value r and p-value l. The corresponding R code looks very similar, except that we use the function pt instead of stats.t.cdf. Because the t-distribution is symmetric, you don't actually need to compute the p-values for each tail separately. Instead, you can compute the area in one tail and then just double that value. I've demonstrated their equivalence below. Here I have output text from Python showing that one-tailed p-value on the left is 0.027906 and a bunch of other numbers. And the one-tailed p-value on the right is almost exactly the same number. There's some very, very small differences after many, many digits. The two-tailed p-value as the sum is 0.055812, and the two-tailed p-value by doubling is the same numerical value. There does seem to be some difference in the two one-tailed p-values, but that is just minuscule rounding error. There is a class of functions called survival functions, which are so named because they're used to determine the probability that a person or device will survive past a certain date. Conceptually, the survival function is simply 1 minus CDF, but the details of their implementation allow for slightly more accurate probability estimates compared to the code I showed above for p-val r. This is illustrated in the online code. Later in this chapter, I will show you how to use Python or R functions to return the t and p values without having to use the CDF or PT functions yourself. But you need to first put in the effort to understand where those values come from before you can take the easy route. Section 11.1.5, t-values from p-values. Now you know how to get a p-value from a t-value and a df parameter. It is conceptually easy to get a t-value from a specified p-value and df. Consider the CDF shown in figure 11.3a. You've been reading this plot as going from the x-axis to the y-axis. That is, finding the y-axis value that corresponds to a specific t-value. Now read the plot the other way. Pick a specific CDF value on the y-axis to discover the corresponding t-value on the x-axis. The plot in panel B shows the axes swapped to facilitate comparison. This paragraph references figure 11.3, which contains two panels, panel A on the left and panel B on the right. Panel A shows a CDF from t-values, with t-values on the x-axis ranging from -4 to +4, and the CDF starting at 0. It makes like a sigmoidal shape curve, and it goes up to 1 as t gets towards around 3 to 4. The panel B to the right is actually exactly the same mathematical function, but the two axes have been swapped. So now the x-axis is the CDF, and the y-axis is the t-value. The idea is that you can obtain t-values from p-values simply by inverting the functions, which you can conceptualize as swapping the two axes. Back to the text. The Python function to invert the CDF is stats.t.isf, which is the inverse survival function, and the corresponding R function is qt. Remember that the survival function itself is 1 minus CDF, so you need to flip the sign of the inverse survival function. Putting this together, you can use the following code to compute a t-value from a specified p-value. The Python code is minus stats.t.isf, with the first input being the p-value and the second input being the degrees of freedom parameter. The R code is qt. The first input is p-value and the second input is the degrees of freedom. Back to the text. But to make things more confusing, remember that 0.05 here means the sum of all probabilities to the left of a particular value. Indeed, the value from the code that I just described is minus 1.771. So if you want to get a positive t-value, you need to enter 1 minus p as the first input. In other words, the following two lines of code will output the same positive t-value. So for Python, the first line of code is minus stats.t.isf, with the input being 1 minus the p-value, and then the degrees of freedom. The next line is stats.t.isf, inputting the p-value and degrees of freedom. The corresponding R code is minus qt. First input is 1 minus p-val, and the second line of code is qt and inputting p-val. I know it's all quite confusing with the minus signs and the two tails. The good news is that you can use Python or R functions to help with the implementation details. The bad news is that the confusion of one versus two tail tests persists, as you will soon encounter. Section 11.1.6, Determining Significance of a t-test. This subsection is a reminder and expansion of what you learned in Chapter 10. The statistical test associated with the t-value is considered statistically significant if a t-value of that magnitude or more extreme has less than a 5% chance of being observed if the null hypothesis were true. Figure 11.4 illustrates this idea. Imagine that we have a t-value of 1.6 with a degrees of freedom of 20. This t-value is not statistically significant because the area of the null hypothesis t-PDF for t greater than 1.6 is 0.0626 or 6.26%. This paragraph references figure 11.4, which visualizes the process of determining significance of a t-value. What we see in this graph is a t-distribution that shows the x-axis or the t-axis from -1 to +4, and we see the t-PDF looks roughly like a Gaussian. It's centered at 0, and then we see at a value of a little bit above 2, there's a vertical dashed gray line indicating alpha divided by 2 equals 0.025. And then there is a downward-facing black arrow at a value of 1.6, corresponding to the t-value, which, as a reminder, is the ratio of the sample mean minus the null hypothesis value divided by the standard error of the mean, which is the sample standard deviation divided by the square root of n. And furthermore, what you can see on this graph is that the area under the curve from 1.6 all the way up to 4 is shaded in dark gray, with an area indicating that this corresponds to 6.26% of the total area of the t-PDF. Given our two-tailed alpha threshold of 0.05, which was the vertical dashed line that I described, this t-value would not be considered statistically significant because there is a 6.26% chance of observing a t-value of 1.6 or larger if the null hypothesis were true. Back to the text. Here's a question to answer before reading the next paragraph. What is the two-tailed p-value associated with this t-value? Based on the text and on inspection of the figure, you might have guessed that the p-value is p equals 0.062. This is wrong. It is an easy mistake to make and reveals the trickiness of one- and two-tailed tests. In fact, the p-value associated with this t-value is p equals 0.125. Consider that the area to the right of t equals 1.6 is 6.26% of the total t-value distribution, but in a two-tailed test, we are interested in the area that is more extreme than the absolute value of t equaling 1.6. That is greater than 1.6 and less than minus 1.6. Each tail contains 6.26% of the total area, and so the area in both tails is 12.52%. Now, with that in mind, now inspect figure 11.5, which shows both tails of the distribution. I hope it's more clear now. There is a 6.26% chance of finding a t-value greater than 1.6 if the null hypothesis were true, and there is also a 6.26% chance of finding a t-value less than minus 1.6 if the null hypothesis were true. Therefore, the p-value associated with the two-tailed test of t equals 1.6 is the sum of both areas, which is p equals 0.1252. In terms of typographical formatting, you could write t subscript 20 equals 1.6, p greater than 0.12. This paragraph refers to figure 11.5, which is the same as figure 11.4, but showing both tails of the distribution. Remember that 11.4 showed the x-axis ranging from -1 to +4. Here, with figure 11.5, the x-axis ranges from -4 to +4. And everything I previously described, so the downward-facing area corresponding to t equals 1.6, and the area to the right of that shaded corresponding to 6.26% of the total t distribution, that is the same on the negative side, so for negative values, but mirrored, of course. Section 11.1.7, Determining Significance by Critical t-values. The procedure described above is to first compute the t-statistic of the data, second, compute the p-value associated with that t-value, and third, label the finding as significant or not based on the p-value. There is another approach that bypasses step 2. Compare your t-statistic to a critical t-value. A critical t-value is the t-value corresponding to a certain degrees of freedom and alpha threshold. For example, the critical t-value associated with a two-tailed p less than 0.05 and degrees of 20 is t equals 2.086. If your empirical t-value is larger than this, then your test is significant at p less than 0.05. You don't actually need to compute the actual p-value. Critical values are old-fashioned. They are a relic of pre-computer days when p-values could not be reasonably computed by hand. And therefore, statistics books came with really long tables that listed critical test statistic values for different degrees of freedom and alpha values. Nowadays, we just have computers compute the p-value for the observed test statistic value. I considered printing a table of critical values here for your horror and enjoyment, but it would take up too much space, and this book is already long enough. You can search the web for critical t-values table. I included this section here more as an historical observation. For your general statistical knowledge, it is good to know what the term critical value means, and I do reference it a few times in this chapter and other chapters. For example, I will call the critical t-value tau in the discussion of sample size calculations in chapter 17. But it's not really something that you'd actually use unless you're a statistician in a post-apocalyptic civilization without electricity. Section 11.1.8, Assumptions of the t-test. There are specific assumptions made by each t-test variant, for example, assumptions about equal variances, which you will learn about later in the chapter. The following list describes general assumptions of all t-tests. Assumption 1, normality. The main assumption of a t-test is that the mean and standard deviation are valid and useful characterizations of these samples. This basically means that the data are roughly normally distributed. If the mean is not a useful characteristic of a data set, then it doesn't really make sense to perform a statistical test on that mean. Fortunately, many non-normal distributions can be transformed into a normal distribution, as you learned in Chapter 6. That said, t-tests are fairly robust to violations of this assumption, especially with sufficient sample sizes. So don't stress about getting your data distribution to be a perfect Gaussian. If the violations are extreme, or if the sample size is small, you can use nonparametric t-tests to evaluate the differences in medians instead of means. Assumption 2, interval or ratio data. As you know from chapters 2 and 4, quantities like mean and standard deviation are valid only for interval or ratio scale data. That said, discrete numeric data and ordinal data might be okay for a t-test if there is a relatively broad range of values and if the sample size is large. Assumption 3, independent observations. The data samples should be independent of each other. This means that the outcome of one observation should not influence the outcome of another observation. Dependencies in the data can inflate the t-value and reduce generalizability of the finding. Autocorrelations are common in spatial, image, and time series data and can be addressed with additional corrections or alternative methods. Assumption 4, random sampling. Related to independence, data should be collected through random and representative sampling, i.e., each member of the population has an equal chance of being sampled. Violating this assumption is not a problem for the math, but it limits your ability to draw conclusions about the population from the sample. Although the t-test is generally robust to violations of these assumptions that I just listed, it is a good habit to check these assumptions in your data. Severe violations can lead to inaccurate results and misinterpretations. You'll see several examples of incorrect conclusions resulting from severe violations of assumptions in the exercises of this and later chapters. Section 11.1.9, Testing for Normality. There are several ways to examine whether a data distribution is normal. You've already learned about visual inspection-based methods like the histogram and the QQ plot. Quantitative analyses for testing a normal distribution involve evaluating the null hypothesis that the data are normally distributed. Therefore, a p-value larger than 0.05 would indicate that we cannot reject H0, which means that we accept that the data are normally distributed. It's one of the few scenarios in statistics where we want a non-significant result. Conversely, if the p-value is less than 0.05, then we reject H0 and conclude that the data are non-normally distributed. Here I will introduce 3 statistical tests for normality. The first test is the omnibus test. This test compares the skew and kurtosis of the data distribution with the values expected for a normal distribution. The test is implemented in the scipy.stats library with the function stats.normaltest. The second test of normality is the Pearson chi-square test. This is implemented in R using pearson.test from the nortest library and evaluates whether the histogram bin counts of the dataset are consistent with counts that would be expected for a normal distribution. The third test for normality is the Shapiro-Wilk test. This test works by comparing the distribution of the data to values that would be expected given a normal distribution with the same mean and standard deviation as the empirical data. It is conceptually similar to a QQ plot, but the comparison is quantitative rather than qualitative. The resulting test statistic value is called W and varies between 0 and 1, with values closer to 1 indicating a closer match to a normal distribution. The Shapiro-Wilk test is called and interpreted similarly to the omnibus test using the Python function stats.shapiro or the R function shapiro.test. As an illustration, I applied both tests to two n equals 100 data sets comprising random numbers drawn from a Gaussian distribution and an exponential distribution. The p-values for the Gaussian distribution were p equals 0.25 and p equals 0.24 for the omnibus and Shapiro-Wilk tests, and were both p less than 0.001 for the exponential distribution. This paragraph references figure 11.6, which shows distributions of two data sets to illustrate tests of normality. We have data set X1, and its histogram is drawn in a black dashed line, and it looks roughly normal, centered around 0. It's not exactly a perfect Gaussian, but it looks normal within some reasonable sampling variability. And then we have the histogram for dataset X2 in a solid gray line, and that is definitely non-normally distributed. It's random numbers drawn from an exponential distribution, so it starts off with a very high probability of finding small values close to 0, and the probability values or the counts of observed values drops precipitously as the data values increase. So again, both tests were significant for X2, the exponential distribution, and non-significant for X1, the normal distribution. Back to the text. Both of these tests are sensitive to sample size. In particular, very large samples can produce a small p-value with only minor and inconsequential deviations from a normal distribution. Therefore, these tests should be used as guides to help you make decisions along with qualitative data inspection. Do not make important decisions about the data only from the p-value of a normality test without looking at the data, especially if the sample size is large. Well, large is a subjective term, but let's say greater than 50. Section 11.2, How to make a t-test significant. It is very noble to say that we don't care how the result turns out. We simply collect data, run the appropriate statistical tests, and then report the results. But the truth is that we all want to get significant results in our research. That's not a bad thing. Wanting to get significant results can help ensure that the experiments are well designed and the data are high quality. And with this in mind, I will explain 3 different ways to maximize your t-value. It's useful to think about the different factors by which the t-value can increase, because you may have control over some, not all, of these factors. To be clear, these are not unethical strategies for manipulating your data to get a desired result. These are aspects of experimental design, data collection, and data cleaning to consider that will increase data quality, which in turn will increase the likelihood of discovering potentially subtle effects. For reference and elucidation, I have rewritten equation 11.1 below. So this is now equation 11.4, and it reads t underscore df equals the fraction x bar minus h naught over s divided by square root n equals the quantity x bar minus h naught times square root of n divided by s. So method 1, increase average differences. Obviously, the larger the numerator of the fraction, the larger the t-value. This is relevant for experiment design because if you anticipate a large amount of variability and/or a small sample size, you should attempt to maximize the magnitude of the mean differences. This paragraph refers to figure 11.7b, which shows 2 curves that depict histograms of 2 data samples in a 2-sample t-test. Now, the distributions in panel A are mostly overlapping. We have a solid black t-PDF and a dashed gray PDF, and they are mostly overlapping with some subtle difference in the means. The panel A is labeled non-significant. Panel B shows the 2 distributions with the same width as in panel A, but the distributions are further apart. So there is a large mean difference. So those distributions have the same variance as those in panel A, but the means are further apart, so the t-test will be significant. Back to the text. Method 2 is to reduce variability. The smaller the denominator, the larger the fraction. If you know that the effect will be modest, you should try to minimize the variability. And you can do this by refining the experiment manipulations, ensuring that the measurement sensors are precise, selecting a more homogeneous sample, and cleaning the data to remove outliers. This paragraph references figure 11.7c, which shows two distributions as in the other two panels, but these distributions are much more narrow. In particular, the two distributions have the same means as those in panel A, which were non-significant, but the variances are smaller, leading to a significant t-test. Back to the text. The third method is to increase sample size. This is the reason why I rewrote equation 11.4 with the square root of n term in the numerator. Increasing the sample size will increase the t-value even if the mean difference and standard deviation remain the same. It is a nonlinear impact, so increasing the sample size has a big effect in small samples, but less effect on larger samples. Increasing the sample size is a good strategy when the data are cheap, but less well controlled. This is a typical strategy, for example, in epidemiological studies that use hospital records. The variability is likely to be large, and the effect size may be small. Think, for example, of the impact of daily vitamins on longevity. But researchers can acquire sample sizes in the tens of thousands. I separated these different components of the t-value because different kinds of research and different kinds of experiments allow for control over different factors. For example, if you are doing clinical research on patients with schizophrenia over 60 years of age, then you will probably have small sample sizes, and you can assume that the variability will be large. So you will need to design the research to look for large effects. On the other hand, if you are conducting market research on whether the color of an advertisement increases sales, you can assume that the magnitude of the effect will be small and the variability will be high, so you will need to plan on collecting a lot of data. Data sets can differ from each other in characteristics other than their means. In fact, there are many descriptive characteristics that are independent of the mean, including variance and higher statistical moments. Although the mean is the most appropriate characteristic to evaluate in many cases, a non-significant t-test does not indicate that the samples do not differ. It indicates only that the means of those samples do not differ. Section 11.3, One Sample T-Test. I hope you found this chapter thus far enlightening. My main goal was to help you grasp the foundational principles that underpin the t-test. That is the crucial conceptual content. The rest of this chapter delves into finer details regarding the adaptation of the t-test formula for various scenarios that I introduced at the outset of this chapter. Let's begin with the one-sample t-test. It is the simplest form of the t-test because it involves only one sample and therefore one standard deviation. The formula is presented in equation 11.5. Equation 11.5 reads T subscript n-1, so T with n-1 degrees of freedom, equals the fraction that contains in the numerator x bar minus h naught, and in the denominator s divided by square root of n. Back to the text. Let's work through an example. The teacher wants to know if the average exam score of her students is significantly different from the national average of 75 points. There are 15 students. These are fake data that I made up for this example. And the text shows all the data, which are 15 integers that range from 65 to 90. Now, before writing any code, we need to translate the hypotheses into a model, a pair of mathematical statements that define the null and alternative hypotheses. For t-tests, the mathematical versions of the hypotheses are usually simple and easy to define. So we have h0 is x bar equals 75, and ha is x bar is not equal to 75. Notice that the test is two-tailed. The mean and standard deviation of this sample are x bar equals 78.1, s equals 7.5. The t-statistic is t sub 14 equals fraction with the numerator 78 minus 0.1 minus 75, and the denominator is 7.5 divided by the square root of 15. This equals 1.624. We can compute the p-value using the CDF of the t-distribution. In this case, t with 14 degrees of freedom equals 1.624, and the p-value is less than 0.127. Because the p-value is larger than 0.05, we cannot reject the null hypothesis. We therefore conclude that the average exam score in this classroom was not significantly different from the national average. Now, even without conducting a formal t-test, you can see that the effect is unlikely to be significant. Consider that the difference between the classroom and national average scores is around 3, which is less than half of the standard deviation. A mean difference smaller than its standard deviation is unlikely to be significant, although it could be in a large sample. You can gain a lot of insight into data just by looking at the descriptive statistics. Python, t-test with the scipy.stats library. The Python function for the one-sample t-test works as follows. T-test equals stats.t-test underscore one-samp, and the first input is x, and the second input is h0. In other words, you input the data set and the h0 value, and the function outputs a variable that here I call t-test. This is not a float, NumPy array, list, or any other data type that you've encountered so far in this book. It is a t-test result object that contains 3 pieces of information we need from a t-test. So if we print out the type of the t-test, the result is class scipy.stats.statspy.t-test result. And when we print out the output of the t-test, we can see the 3 values: statistic equals 1.62, p-value equals 0.12, df equals 14. Back to the text. I've truncated the output so it would fit on the page. The t and p values are calculated to a ridiculous precision. Importantly, you can see that those values match what I wrote earlier. Computing a t-test in R. The R base environment comes with a t-test function. You don't need to install or import separate libraries. The code is t-test equals t.test, and the first input is x, and the second input is mu equals h0. In other words, you input the data set and the h0 value, and the function outputs a variable that here I call t-test. Again, this is not a float, array, data frame, or any other type of data that you have encountered so far in this book. It is an h-test object that contains the 3 pieces of information we need from a t-test. So if we print the class of this variable t-test, we see that the class is a one-sample t-test. And if we print the content of that variable, we see that it contains the following lines: data equals x, t equals 1.624, df equals 14, p-value equals 0.1267, alternative hypothesis, true mean is not equal to 75, 95% confidence interval is 74 to 82.2, sample estimates, and the mean of x is 78.13. Back to the text. The variable t-test prints out a lot of useful information, including the t and p values and 95% confidence interval around the mean. You'll learn more about confidence intervals in Chapter 13. You can extract individual elements in that object using, for example, t-test $p.value. Section 11.4, Two-sample t-tests. Two-sample t-tests are used to evaluate whether the mean of two samples are significantly different. The general formulation of the null and alternative hypotheses are H0 is x bar equals y bar, HA is x bar not equal to y bar. It is sometimes useful to think of the hypotheses as equations set to 0. H0 is x bar minus y bar equals 0. HA is x bar minus y bar not equal 0. Two-sample t-tests come in two flavors: paired samples and independent samples. Section 11.4.1, the paired samples t-test. The paired samples t-test is also called dependent t-test, is used when the two samples come from the same individuals. This is common for experiments in which an intervention or manipulation is introduced and people are measured before and after the intervention. A few examples. Footnote. Proper experiment design for these examples should include a placebo or control condition, but let's ignore that in the interest of simplicity. Example 1. Anti-aging supplement. A research lab is testing whether a newly developed molecule slows biological aging. The paired samples t-test would compare the average telomere lengths before and after treatment. Footnote. Telomeres are DNA snippets that protect chromosome boundaries. They shorten with age and predict negative health outcomes and therefore are used as biological markers of aging. Example 2. Flipped classroom model. A teacher switches from the traditional classroom model, lectures during the day and homework in the evening, to a flipped classroom model, video lectures in the evening and individual/group work during the classroom period, to determine whether test scores improve. The paired samples t-test would be used to compare the average difference in test scores before and after implementing the new teaching method. Example 3. Background noise on reading comprehension. A researcher wants to investigate the effect of background noise on reading comprehension. Participants answer true-false questions based on text that they read with and without background auditory noise. The paired samples t-test would be used to compare the average difference in reading comprehension scores between the quiet and noisy conditions. A paired samples t-test is implemented by subtracting the two data values from each individual and then performing a one-sample t-test exactly as described in the previous section. This is not only a simple method, but is also quite powerful because it reduces the variability in the data. I will demonstrate this with an example. Let's continue with the reading comprehension study. Imagine that comprehension test scores range from 0 to 100, and I'll use XN and XQ to indicate the comprehension scores in the noisy and quiet conditions. Here are the data. Both samples had Shapiro-Wilks p-values greater than 0.05, and these are all fake data. I'm not going to read out all of the numbers, but there are 10 integers for each data set, so XN and XQ, and the numbers vary between around 20 up to around 95. Back to the text. Visual inspection of the data reveals a large amount of variability in the scores, indicating that our research participants have very different baseline reading comprehension abilities. But we get a different sense of the data when we examine the difference scores. I'll call that variable delta equals xq minus xn. So here we have data set delta, capital Greek letter delta, equals, now these are 10 integers and they range from -6 to +10. This paragraph references figure 11.8, which shows two scatter plots. In panel A, we see the raw scores for the two reading conditions. There are two columns of data, xn and xq. The y-axis ranges from 0 to 100, and each individual data point is indicated as a gray circle with lines connecting the corresponding individual from the xn condition to the xq condition. And then we have panel B, which shows the change in comprehension scores. So capital delta equals xq minus xn. Now, the difference scores in panel B also range from around -50 to +50. So the total span, the numerical span in both axes, in both panels is the same, but you see that the visual range, the dispersion of the numerical values of the data is much larger when looking at the raw data in panel A compared to the differences in panel B. Back to the text. The difference scores are shown in figure 11.8b. Notice that both y-axes have the same range, so spanning 101 units, so the variabilities in the two plots are directly visually comparable. In other words, although baseline reading comprehension is very different between individuals, the change in reading comprehension due to background noise is comparable across individuals. This highlights the power of within-subjects analyses for reducing variability. This is a theme that will reappear when you learn about repeated measures ANOVA. By the way, why did I compute capital delta as xq minus xn and not xn minus xq? As I mentioned earlier in this chapter, the order of the subtraction does not matter for the statistical significance of a two-tailed t-test. Although the sign is statistically arbitrary, the order can facilitate interpretation. In this example, I expect that comprehension will be higher in quiet compared to noisy backgrounds, so I set up the equation such that a positive t-value would correspond to an increase in performance in a quiet environment. Had I computed capital delta equals xn minus xq, we'd expect a negative t-value, which we'd interpret as a decrease in performance in a noisy environment. Perhaps you prefer that interpretation. Now that we've reduced the data from two samples into one, we proceed exactly how we did with the one sample t-test. In this case, H0 is capital delta bar equals 0, and HA is capital delta bar not equals 0. With these numbers that I made up, the result is T with 9 degrees of freedom equals 2.023, P less than 0.074. In other words, the t-test is not statistically significant. Let's imagine that these are real data for a real PhD dissertation. What do we do with this p-value? It is not statistically significant at the accepted alpha level, but it is close. And when looking at the different scores, capital delta, and in figure 11.8b, there are only two individuals who showed a negative change. Now, I could sit here on my high horse inside the ivory tower, give you a patronizing look and say, it is not significant, end of story. But the truth is that this study has important implications for education and society. For example, libraries, offices, co-working spaces, not to mention the importance to the junior researcher who needs this study for their dissertation. It does, quote unquote, look like there is a real effect in the data, and the direction of the effect is consistent with common sense. Now, some people will be tempted to try various tricks to get the p-value down, like removing a participant or trying various Data normalizations until something works. You will get to explore this in exercise 7, or different ways of calculating the comprehension scores. These are all dangerously close to p-hacking, which refers to unethical, manipulative statistical practices to obtain a desired result. One ethical approach, for example, would be for the researcher to double the sample size and not perform statistics again until the final sample is collected. I will have more to say about this topic in Chapter 18, but I wanted to introduce the issue now. Missing data. Because the goal of a paired t-test is to evaluate a change in a variable, missing data are extremely problematic. As a reminder of the discussion about missing data in Chapter 7, there are two options to deal with missing data in a paired samples t-test. Option 1, row-wise removal. Remove all data from any individual with one missing data value. This is a good option when you have a large data set and can afford to lose data. Option 2, imputation, or replace with interpolated values. This involves quote-unquote guessing the missing data value based on the mean of other individuals or based on a regression or machine learning model. To be honest, neither of these options is very savory. My preference is row-wise removal because I am slightly uncomfortable with making inferences based on data that are modeled instead of measured. But that's my opinion and intuition, and not everyone agrees with me. Either way, if you anticipate a large amount of missing data before running the study, try to maximize the amount of data you collect. Having a large data set will help with both missing data strategies. Section 11.4.2, Independent Samples t-test. An independent two samples t-test, also called an unpaired t-test, evaluates whether the means of two separate groups significantly differ. This is different from the paired samples t-test, where the same individuals are measured twice. Indeed, the sample sizes might differ between the two groups. Here is an example of when an independent samples t-test would be appropriate. A startup company that makes a card-playing app has two user interaction designs and wants to know which leads to higher engagement times. They randomly assign 50 people to use design A and 40 people to use design B. The DV is time spent on the app. Because the two samples come from different individuals, the t-test needs to account for possible differences in standard deviations and sample sizes. Equation 11.9 shows a formula that separates the sample sizes and variances for each group. This is also called Welch's test. Equation 11.9 reads T equals the fraction, the numerator is x bar minus y bar, and the denominator is capital theta. And then we have capital theta defined in equation 11.10, and that is the square root of the sum of two terms. The first term is x squared sub x divided by n sub x, plus the second term, which is s squared sub y divided by n sub y. Back to the text, where s squared sub x is the sample variance of variable x, and n sub x is its sample size. In fact, this is not the only formula for a two samples t-test. There are several variants of this formula that are applied depending on whether the two groups have equal sample sizes and/or variances. Please take a moment to simplify the capital theta term, assuming that the variances and sample sizes are equal. You will find that the t-value reduces to a similar expression as that of the one sample t-test. You can also simplify the denominator, assuming equal variances but unequal sample sizes. In practice, you instruct the relevant Python or R function to assume equal or unequal variances. Degrees of freedom. If the variances are roughly equal, the df are n sub x plus n sub y minus 2. If the variances are unequal, a correction factor is applied, which leads to a more complicated df formula. I will show this formula in exercise 9, but essentially it involves adjusting the n terms according to the variances. Testing for equal variances. The statistical lingo for equal variances is homogeneity of variances. The opposite, unequal variance, is called heterogeneity of variances. The question is, how do you know whether the two groups have quote-unquote equal variances? Of course, due to sampling variability, the variances won't be exactly equal, even if they're drawn from populations with equal variances. Therefore, the question is whether the variances are close enough to assume homogeneity. There are 3 ways to determine whether the variances are equal. One is to visualize the data and make a qualitative determination. This is feasible when performing a small number of tests. A second method is to use the quote-unquote doubling rubric, which means to determine whether the standard deviation from one group is less than twice the standard deviation of the other group. In other words, if S sub max is less than 2S sub min, then you can assume homogeneity of variance. The third and most rigorous method is to use Levene's test, which evaluates the null hypothesis that S sub 1 equals S sub 2. Footnote: there are other inferential statistics for testing homogeneity of variance. Levene's is a common one. Back to the text. I won't present the math of Levene's test here, but it is based on the principles of a one-way ANOVA. If Levene's test is non-significant, that is, if p is greater than 0.05, then you can assume homogeneity of variances. An example. Let's work through an example. I created 2 groups that differed in means, standard deviations, and sample sizes. And just to keep things interesting, I drew them from different distributions. One sample comprised 50 numbers drawn from an exponential distribution, and the other comprised 42 numbers drawn from a Gumbel distribution. This is demonstrated in the online code. You can see the data values and their histograms in figure 11.9. This paragraph references figure 11.9, which shows data from 2 independent samples. We have 2 panels, one on the left labeled data, and one on the right labeled distributions. Panel A shows a scatter plot with 2 columns, x1 and x2. The numerical values on the y-axis range from around -2 to +17. We can see the data for x1 are more broadly distributed across the range of the y-axis, and the data values for a variable x2 are more constrained to around y equals -2 to maybe y equals 4. In panel B, we see histograms of these 2 distributions. The histogram for distribution x1, that's the one with larger variance, that has a wider spread. It's also skewed to the right. So you see that there are many values with small data values and fewer data points as the data values get larger towards and above 15. And then we have the data for variable x2 that looks roughly normally distributed, although it doesn't quite go down to 0 towards the left. Back to the text. Panel A allows us to perform the visualization check for homogeneity of variance. The variance certainly looks larger for x1 compared to x2. The doubling ratio is only 1.74, but the Levene's test has a p-value of 0.005. Remember, the Levene's test has h0 is s squared sub 1 equals s squared sub 2, which means that we reject the null hypothesis of variance homogeneity, ergo we assume that the variances are unequal. Now with sampling variability and these sample sizes, Running the code multiple times will sometimes produce variance homogeneity and sometimes variance heterogeneity. I also tested both samples for normality. These tests were somewhat inconsistent in that some random datasets had evidence for normality, while other random datasets had evidence against normality. Furthermore, the conclusions of the Shapiro and omnibus tests were not always consistent with each other. In the case of the data shown in figure 11.9, that's the figure I recently described, the p-values were 0.03 and 0.18 for datasets X1 and X2. Nonetheless, t-tests are fairly robust to minor violations of the normality assumption. Now let us proceed to the t-test assuming unequal variances. Python and R code implementations look like this. In Python, we have the function stats.ttest_int, and then 3 inputs. The first input is data1, second input is data2, third input is equal_var equals false. The R code is t.test, and then we have 3 inputs, data1, data2, and var.equal equals false. Notice the syntax for specifying unequal variances. The default value of equal var is true. Also notice that R uses the same function for the 1-sample and 2-sample t-test. Providing 2 datasets as the first 2 inputs indicates to R that you want to perform a 2-sample t-test. Margin note. The degrees of freedom of this test is 90 because the 2 samples have 42 and 50 observations, and n sub 1 plus n sub 2 minus 2 equals 90. Back to the text. The results were t sub 90 equals 5.95 with p less than 0.0001, meaning that the means of the 2 groups are statistically significantly different. What does this result signify, given the data? X1 is non-normally distributed, so it is questionable whether the mean is really a useful description of the data. Nonetheless, visual inspection of the data clearly shows that data X1 has larger values than X2. Now, a log transform could make X1 more normal, but it might make X2 less normal, and we cannot transform one variable without transforming the other because this would trivially change their means. I believe that in this case, the t-test is useful even if the data do not appear to be a textbook example of ideal circumstances. Reality is rarely ideal, and so applied statistics books should embrace complexity and ambiguity. You might be wondering whether it really matters if we assume equal or unequal variances. In this example, the t-test result was highly significant regardless of this assumption, and you'll have the opportunity to explore the impact of equal variance assumption in exercise 9. Section 11.5, Effect Size. An effect size is a quantitative measure of the magnitude of the observed effect. There are 2 measures of effect size in t-tests, Cohen's d and r². In this section, I will describe and define these metrics and then discuss how they are related to the t-value. Cohen's d. Footnote. Unrelated. Back to the text. Cohen's d is calculated as the difference between 2 means divided by a standard deviation. It provides an estimate of the magnitude of the difference between the 2 groups under study, transformed into standard deviation units. The formulas are below. D sub 1 indicates Cohen's d for a 1-sample t-test, D sub p indicates a paired sample t-test, and D sub 2 indicates a 2-sample t-test. Here we have 3 equations. Equation 11.11 is D1 equals a fraction with the numerator x bar minus h naught, and the denominator is s. Equation 11.2 reads d sub p equals the fraction x sub a bar minus x sub b bar, and the denominator is s sub delta. Equation 11.13 reads d sub 2 equals the fraction x bar minus y bar divided by some long term that incorporates both the sample sizes and the standard deviations of the two groups for x and y. Back to the text. In equation 11.2, s sub delta is the standard deviation of the difference. Now, these equations look very similar to the equation for the t-test, except without the square root of n factor. Indeed, Cohen's d is basically the t-value, but using the sample standard deviation instead of the standard error of the mean. That leads to an important distinction between effect size and t-value, which I will discuss more later. Cohen's d has units of standard deviation, so you can interpret this measure of effect size in the same way that you would interpret a z-transformed variable. Although Cohen's d can be negative, it is customary to take the absolute value or arrange the numerator to get a positive result. For some reason, people are uncomfortable with negative effect sizes. R squared. R squared is also called the coefficient of determination and is a different measure of effect size. You'll see R squared appear several times in statistics, including correlation, regression, and ANOVA. The formulas and interpretations differ slightly by application. In the context of the t-test, R squared represents the proportion of variance in the data that is attributable to the deviation of the sample mean from the h0 value. Here we have equation 11.14, which reads r squared equals the fraction t squared, and in the denominator we have t squared plus df. Back to the text. R squared is a value between 0 and 1, where 0 indicates no effect, so t equals 0, and values closer to 1 indicate a stronger effect. For a t-test, r squared can never truly be 1, because there will never be 0 degrees of freedom. Nonetheless, as the t-value increases relative to the degrees of freedom, r squared will approach 1. Cohen's d is more commonly reported than r squared, in part because it was more commonly reported in the past. In statistical reporting, like in real life, traditions maintain inertia. Anyway, you will discover in exercise 11 that these two quantities are closely related. Section 11.5.1, Effect Size versus T-Value. Effect size and t-value are different but complementary quantities. The t-value is a measure of the departure from the h0 t-value distribution and, when transformed into a p-value, indicates how unlikely the observed data would be if the null hypothesis were true. On the other hand, the effect size is a measure of the magnitude of the effect, regardless of its probability relative to an h0 distribution. The key difference between the t-value and Cohen's d is the scaling by square root of n in the t-value. This means that Cohen's d is not directly translatable to a p-value without knowing the sample size. But a more important implication is that a large t-value might result from a large sample size, even if the effect size is small. This decoupling between statistical significance and effect size has important implications for interpreting statistical significance and is the focus of exercise 11 as well as other exercises in later chapters. One way to think about the distinction is that the t-value is a measure of statistical significance, while Cohen's d is a measure of practical significance. Section 11.6, nonparametric t-test alternatives. Nonparametric t-tests involve comparing medians instead of means. You can use these tests when the data strongly violate the normality assumption and when data transformations are not desirable, or when the data contain outliers that you do not want to remove because they are valid though non-representative. It would be nice if the formulas were as simple as replacing the mean with the median in all the equations presented in this chapter. Unfortunately, non-parametric tests are based on algorithms that are more complicated and less intuitive. Fortunately, the use and interpretations of these tests and their p-values are the same. The methods presented in this section are not formally t-tests because they do not produce a t-statistic, nor are their test statistic values evaluated against a t-distribution, but they have the same function as a t-test, evaluating whether the central tendency of the data differs from a pre-specified value, so they are considered non-parametric alternatives to the t-test. Section 11.6.1, Wilcoxon signed rank. The Wilcoxon signed rank test, also called the Wilcoxon test or the signed rank test, is a medians-based replacement for the one-sample t-test or the paired t-test. Different statistical programs implement the Wilcoxon test using slightly different procedures and algorithm modifications. The following steps describe the general algorithm for the Wilcoxon signed rank test, but the precise details differ between Python, R, and MATLAB. The summary version is that if the data were evenly distributed around the null hypothesis value, then the number of data points to the left of H0 should equal the number of data points to the right of H0. Step 1. Remove data points that equal the H0 value for a one-sample t-test or pairs that are equal for a paired samples t-test. The reason is that these values do not provide evidence for or against the null hypothesis. Step 2. Compute the difference between each data point and the null hypothesis value for one sample test, or between the pairs of data points for a paired samples t-test. Step 3. Rank transform the absolute values of those differences and sort the ranks in ascending order. Multiply these ranks' absolute differences by the signs of the data from step 2. Essentially, this involves multiplying the ranks from the data below the null hypothesis value by -1. These are the quote-unquote signed rank values from which this analysis gets its name. Also, Professor Frank Wilcoxon. Okay, let's call this result of this step variable R. Step 4. Count the number of negative R values and the number of positive R values. The smaller of these sums is called W, and in R, this variable is termed V. Step 5, transform W, or V in R, into a Z value from which a P value can be obtained. The transformation is done through a somewhat complicated formula that is printed in the book, but which I am not going to explain in detail here in the audio version. Suffice it to say, we have the output of a computation that gives us a value for Z. And this Z-score can be interpreted as a standard Z-score to which a p-value can be associated, and that p-value is the significance of the Wilcoxon signed rank test. I have an example for you. I created non-normally distributed data as x squared for x drawn from a standard normal distribution, and I tested against the null hypothesis value of H0 equals 1. I then computed the Wilcoxon test using the following code. In Python, it is stats.wilcoxon, and then 2 inputs. The first input is data minus H0, The second input is method equals approx, with approx in single quotes. The corresponding R code is wilcox.test, and then with the two inputs being data minus H0 and exact equals F. In these data, the z-score was minus 0.95, which had an associated p-value of 0.341. This is greater than the threshold of 0.05, so we do not reject the null hypothesis. The empirical median is not statistically significantly different from h0 equals 1. This paragraph references figure 11.10, which shows an example of the Wilcoxon rank sign test on non-normally distributed data. There are two panels arranged in a row. The left panel, panel A, is termed data. Here we see a scatter plot with the x-axis containing data index varying from 0 to 100. The y-axis ranges from a little bit below 0 to around 5, and we see lots of gray circles plotted throughout. There is a large concentration of data points with small values around 0, and a relatively sparse collection of data as the data value increases going up the y-axis. We see a dark black line, horizontal line, indicating the data median at approximately 0.4 maybe, and there is a horizontal dashed gray line indicating the null hypothesis value at y-axis equals 1. And then on panel B, we have a histogram of the same data that I just described. The histogram shows a power law distribution. So most of the data values have very small values close to 0, and a smaller number of data values are larger than 0. And we also see vertical lines corresponding to the median and the null hypothesis value. Back to the text. A few notes about implementing the Wilcoxon test using the Wilcoxon test functions. Note 1. This function evaluates the null hypothesis that the median of the data is 0, i.e. that h0 equals 0. Therefore, you need to input a data vector that has already been shifted by the null hypothesis value. That is, set x tilde equals x minus h0, as I showed in the code. So that was data minus h0. Note 2. However, for a paired samples test in Python, input both data vectors separately. For example, stats.wilcoxon x, y. In R, you can input both data vectors, but you need to specify that the variables are paired. For example, wilcox.test x, y, paired equals true. You can equivalently subtract the vectors and then input one vector. For example, input x tilde equals x minus y. Note 3. The Python function outputs the w value and its p value. If you want a z value, use the optional input method equals approx. See online code. R only computes the z value internally and does not return it as an output value. So if you want the z value, you can convert the p value into a standard z-score. Note 4. There are some minor differences in implementation among different software packages like Python versus MATLAB versus R. Confusingly, Python takes the smaller of the signed rank count, which means that the z value will be negative even if most of the data points are above the h0 value. In practice, you need to compute the empirical median and/or visualize the data to determine whether the concentration of data points is left or right of the h0 value. This paragraph references figure 11.11. This margin figure illustrates that the Wilcoxon Z in Python reflects the negative asymmetry around the h0 value. Here we have two panels showing two scatter plots of random data. In the top panel, most of the data values are to the left of the H0 value, which is indicated as x equals 0. So most of the dots are negative. And the Wilcoxon Z is minus 4.23. In the lower panel, we see the reverse situation. So most of the data points are positive above the null hypothesis value of 0, and yet the Wilcoxon Z is still minus 3.73. Section 11.6.2, Mann-Whitney U-test. This test is variously called the Mann-Whitney U-test, the Mann-Whitney Wilcoxon U-test, or the Wilcoxon rank sum test. It is a median-based alternative to the independent two samples t-test, and it can be used on any numerical data type and for data with any distribution shapes and characteristics. After some deliberations, I decided not to describe the algorithm in as much detail here as I did with the Wilcoxon test, because it is more involved than the sign rank test, and I don't think it provides much additional insight into the nature or interpretation of the test. Briefly, the test is based on ranking the combined data from both groups. A variable u encodes whether the ranked observations in one group tend to be higher than the ranked observations in the other group. This variable u is then transformed into a z value that is normally distributed under the null hypothesis that the medians of the two groups are equal. The corresponding p-value is used to determine the statistical significance of the Mann-Whitney U-test. Because the Mann-Whitney U-test is based on medians and ranks, you don't need to worry about variance or normality assumptions like with the independent two samples t-test. An example: I applied the Mann-Whitney U-test to the data I use to illustrate the independent t-test. Now, we already know from the normality tests that random data from these distributions are sometimes non-normally distributed, which justifies the use of a non-parametric test. The test is easy to implement in Python. Python code is stats.manwhitneyu, and then the two inputs are data1 and data2. In R, you use the same function as for the Wilcoxon test, but you provide two input variables. So wilcox.test, and then two inputs, data1 and data2. Reminder that the difference in R between a paired samples Wilcoxon test and a two samples Mann-Whitney U-test is the optional third input, paired equals true. The default setting is paired equals false. The p-value for this test was very small, indicating that the medians of the two distributions are statistically significantly different from each other. Section 11.6.3, Permutation Testing. Another non-parametric alternative to determining the statistical significance of a t-test is to use permutation testing. Permutation testing for t-values has several advantages for data that contain outliers or are non-normally distributed, or for applying corrections for multiple comparisons when there are many tests to perform in correlated data. Chapter 16 is dedicated to permutation testing, so I will postpone a detailed elucidation until then. Section 11.7, More than two samples. The t-test variants I introduced in this chapter are for one or two samples. What do you do if your experiment design has more than two samples? Perhaps you have data from a medical experiment that compared 3 different medications in 2 different patient groups. That's 6 groups in total. Now, you might think of running a series of t-tests to compare all pairs of samples. So that would be 14 two-sample t-tests in the example above. Although this is technically possible and very occasionally acceptable, it leads to a multiple comparisons problem and can incorrectly specify the variance of paired samples. It also limits the ability to test for interactions between experiment factors. For example, if the effect of medication depends on the patient group. Therefore, if you have more than 2 samples to compare, the appropriate analysis is an ANOVA. Section 11.8, Exercises. As you know, I do not read the exercises out loud in this audiobook. Please see my YouTube channel for a longer elucidation of the exercises and their solutions. End of chapter 11.